Hello students. So today we start the interference, which is the next topic of next unit of our syllabus. So to start with the interference, I will go startingly with this interference in thin film. This is a very essential topic to get the benefit in the derivations of Newton's ring and obviously in the Michelson interferometer. These are the upcoming topic. So first let us discuss interference in thin film. So what is the agenda of this talk is that we will discuss the phase changes due to reflection. Then we go to the phase change due to path length difference. Then we'll discuss little bit of thin film interference, and then I'll provide one of the example. How can we solve few of the numerical problem based on thin film interference? So this is a beautiful picture of the thin film interference. You can see the variety of the colors, which is usually we can see in our water droplets or maybe in the soap drops also. So this is what the thin film you can say, and this is a thin film interference, and that is because of the phase difference of reflected wave due to path length differences. So film is there, right? And the phase difference of the reflected wave due to reflection of a higher N material. So two kind of thing: the phase difference due to the path length difference, and phase difference which is because of the reflection due to a higher N material. Higher N means this is higher refractive index material. So this is what thin film interference. Let we have this air and we have the film. That film contains this T thickness, and let that refractive index of air, which is usually smaller than the refractive index of film. So this is what the picture, and what will happen that when the light will enter here in this way, that the red light is coming there, and then it will be reflected from this surface where the air and the film meets. So from this surface, since air is having lower refractive index than the refractive index of the film, then there must be a phase change, and which would be 180-degree phase change. So to going back, so when the light will be reflected here, light will come to this surface, it will be reflected from here, and ray 1 will undergo with a phase change of reflection. So this ray 1 will contain 180-degree phase change because of the reflection from rarer to denser medium. Then this ray will refracted back also in the film, and then it will reflected from this particular point. And definitely now this time this ray is going there, but this air is having the rarer medium comparative to film. The case is different. The wave is coming from rarer to denser. Now the ray is going from denser to rarer, and this time there would be no phase change. So two kind of reflection. One is from the denser surface. Second one is from the rarer surface. So this time there will be no phase change. So once this ray 2 will go back here, and we will have no change in the ray 2. So you can say that ray 2 does not undergo a phase change on reflection, whereas ray 1 undergoes with a phase change on the reflection. So due to reflected ray 1 and 2, now the interference will be there because of this phase change in the between 1 and 2. And this pattern will remain continue. So we will have the variety of the reflected system waves. Now the wavelength in the film is different than in air. This is definite. So assume that the incident light is nearly perpendicular to the film surface. So we can say this lambda film means this lambda is there obviously, but the lambda will be different in this in this film. So lambda film will be lambda upon n of the film. So this n is the refractive index. So we'll keep on this one. Lambda film will be n of the lambda film. Then the path length difference is approximately 2t. Look there. So this is the extra path which is traveled by this particular ray number 2. Because ray number 1 is reflected from here, ray number 2 is reflected from here. So in addition to the phase change, if you go with the path length, so this ray 2 will travel this and this path more while going back, and this is approximately equal to 2t. If this we consider this ray which is perpendicular to the thin surface, so this will travel approximately 2t more distance. So there is a 180-degree phase difference. This is due to the first reflection and 2t also. So we will get destructive interference if suppose we have destructive interference when the path difference is an integral multiple of wavelength. So what will happen if we consider the path difference? So path difference would be 2t and plus this lambda by 2. So 2t plus lambda by 2. So it's 2t plus lambda by 2 and that should be half of the integer. So this half of the integer which is needed for destructive interference will be cancelled out. So ultimately we'll get 2t equal to n lambda film. This n lambda film is equal to lambda by n film. So 2n film t equal to n lambda. So this is the formula for interference in film, and this formula will produce the destructive interference here for m equal to 0, 1, 2, etc. Similarly, for to get the constructive interference, now this 2t plus lambda by 2 should be equal to an integer multiple. So ultimately, the lambda by 2 here will go to the right hand side. It will give you the half integer. So if the path difference is lambda film by 2, 3 lambda film by 2, 5 lambda film by 2, then we will have the constructive interference. So we have the constructive interference when this 2t is m plus half lambda film, or m plus half lambda by n film, or 2n film by m plus half lambda. So it should be very much clear. To get the constructive interference from the interference in thin film, we will have this half integer, odd half integer, that will give us constructive interference. And if we have this integer, only integer, then we will have the destructive interference. So these two conditions are mentioned here. This is for destructive interference and this is for constructive interference for the wave 1 and wave 2. So we can apply the reasoning here to drive this success of the terms. So there are only true when the film is surrounded by a medium with lower index of reflection than the film. Moving further, we have to put a caution there that they are valid when the light is incident almost perpendicular to the film, because we have taken it approximately 2t. So it should be very much cautious that we plan any of the experiment in such a manner that the light goes perpendicular to this particular thin film. If suppose it is not the case, this is the caution. And if suppose this is not the case, we have the light which is not exactly perpendicular to us. So what we have to consider, we have to consider this extra path which may be more than t. This path should be more than t, and obviously this path which is because of this ray 1 will travel more. So for truly perpendicular incidence, you have to take into account the extra path length of the ray reflected at the air film interference, as well as the extra path length which is inside the film, because the path is not perpendicular to the surface. So we have to take the caution. There are some examples by which this is the oil on any of that liquid, then you can see this create a film, and we can easily see the interference because we are having this variety of colors there, destructive and constructive interference. This is again the oil which is there, and on a glass plate, similarly on butterfly. This is a very thin example of some of the thin film. So now how can we solve the interference problem, thin film interference problem? So first we'll identify the thin film causing the interference. Then we will identify the first thing, either the phase difference is due to the path difference, or phase difference because of the phase changing up to the reflection. So this is low to high or change. If suppose the interference is from low to high refractive index, then the change will be high. And we will determine the phase difference due to reflection between the portion of the wave reflected at the upper surface and the portion reflected at the lower surface. Then we determine the phase difference due to the path length, if suppose there is. So two kind of differences. One due to the surface, second one due to the path length, which is traveled more by any of the ray. And then we consider the total phase difference, and then if suppose the total phase difference is an integer multiple, then we will have the constructive interference. If the total phase difference is the half integer multiple, then we will have a destructive interference. I will put an example there. Let a glass lens is coated. That this is a glass lens which is coated. This is a glass lens having this refractive index of glass 1.5. So it's coated one side with a thin film of MgF2. So this MgF2 is the thin film, and this thin film is coated to reduce reflection from the lens surface. So the index of reflection for MgF2 is 1.38. For the glass, it is 1.50. So the question is that what is the minimum thickness of MgF2 that eliminates reflection of light of wavelength lambda equal to this? Assume approximately perpendicular angle of incidence. So it's very simple. This is given that the ray is perpendicular. So lambda is given, MgF2 refractive index is given, glass refractive index is given, air's refractive index is given, and what is asked? The ask is that we have to find the thin film, the minimum thickness of this thin film MgF2, which can eliminate reflection of light. So we want reflection will be there, but we want to eliminate reflection. We want to minimize the reflection, and that will only happen when we will deal the interference which should be destructive. Is it clear to everybody? Because you want that the reflection should be minimum. So reflection should be minimum when the interference here, which will occur from the reflection, will be a destructive interference. So towards this side, no energy will flow, or the minimum energy will flow, and the most of the energy will go towards the refracted side. So that is what the requirement of this numerical. So this is the ray, 180-degree phase change will be there. Second ray, no phase change will be 180 degree. Again, I am just coming back to this point. Look there, this is different from the previous one, because at the previous diagram, that was okay, 180-degree phase difference. But here we were considering, because from there thin film, the light was going towards the air, but now from here the light is going ultimately towards the again the more denser medium. So once again the ray 2 will have the 180-degree phase change. So what will happen? The ray 1 is again having the 180-degree phase difference. Ray 2 will have again the 180 phase difference. So you can see that the ray 1 and ray 2 are similar, because both of them has the same phase difference, because this phase difference is due to the reflection from the denser surface. So there is no need to consider this kind of phase change. So both ray 1 and 2 experience a 180-degree phase shift on reflection. So the total phase difference is due to the path difference. If suppose there is no glass, there was air, then we have to consider the phase change due to the reflection. But nowadays there is no need to get the reflection due to the phase difference due to the reflection. So the reflected light is minimum when the two light, 1 and 2, meet the condition for destructive interference. So path length difference is a half integer multiple. We again say, so we need a half integer multiple, because to get the destructive interference, and this path is now only 2t. There is no need to get this lambda by 2, or because the phases are both the same. So 2t must be equal to m plus half lambda by n mgf2. And since we require the minimum, so to get the minimum, this m should be equal to 0. So 2t is equal to lambda by n gf2, and we can put this value lambda is 550 nanometer as provided, mgf2 refractive index is provided, and this t minimum comes out to be 99.6 nanometer. So this suggested that if suppose we want to coat this glass with this mgf2 film to stop the reflection or to minimize the reflection from this glass surface, so this mgf2 should be of this thickness 99.6 nanometer. This is also referred as anti-reflection coating, and we usually perform this kind of anti-reflection coating to reduce the reflection from the glasses which we wear. Thank you very much. Tomorrow we will go towards the interference in Newton's ring.